Welcome to aminacademy.com. In astronomy, let us discuss about the laws of planetary motion. At about the time that Galileo was beginning his experiments with falling bodies, the efforts of two other scientists dramatically advanced our understanding of the motions of the planets. These two astronomers were the observer Tycho Brahe and the mathematician Johannes Kepler. Together, they placed the speculation of the Copernicus on a sound mathematical basis and paved the ways for the work of Isaac Newton in the next century. The Tycho Brahe, born on December 14, 1546, was a Danish astronomer whose work in developing astronomical instruments and in measuring and fixing the position of stars paved the way for future discoveries. His observations, the most accurate possible before the invention of the telescope, included a comprehensive study of the solar system and accurate position of more than 777 fixed stars. Brahe made a continuous record of the position of the Sun, Moon, and planets for almost 20 years. His extensive and precise observations enabled him to note that the position of the planets varied from those given in published table, which were based on the work of Ptolemy. Next, Johannes Kepler, born 1571, was a German astronomer and mathematician, most famous for creating what was at that point of most accurate model of planetary astronomy with his three laws of planetary motion. Kepler was the first to present a coherent theory that the planets move around the Sun in elliptical orbits, that the speed of each planet varies and that the Sun is responsible for the variation. Johannes Kepler was born into a poor family in the German province of Württemberg and lived much of his life amid the turmoil of the 30 Years' War. He attended university at Tübingen and studied for a theological career. He learned the principles of the Copernicus system and becomes converted to the heliocentric hypothesis. Eventually, Kepler went to Prague to serve as an assistant of Brahe, who set him to work trying to find the satisfactory theory for planetary motion. First, we'll discuss about the three laws of planetary motion. First law, the path of the planets about the Sun is elliptical in shape, with the center of the Sun being located at one focus. This is called a law of ellipses. The second one, an imaginary line drawn from the center of the Sun to the center of the planet will sweep equal areas in equal intervals of time. That is laws of equal areas. Third law, the ratio of the squares of the period of any two planets is equal to the ratio of the cubes of their average distances from the Sun. That is law of harmonies. We'll discuss further detail about laws of Kepler. First law, the law of orbits. According to Kepler's first law, all the planets revolve around the Sun in elliptical orbits having the Sun at one of its foci. The point at which the planet is close to the Sun is known as perihelion, about 147 million kilometers from the Sun, and the point at which the planet is farther from the Sun is known as aphelion, nearly about 152 million kilometers from the Sun. It is characteristics of an ellipse that the sum of the distances of any planet from two foci is constant. Look at here, this is an ellipse, standard ellipse. A Sun is at one focus And look at here, this is a perihelion fastest motion, aphelion the slowest motion. Now we will discuss further about this. Now we will discuss about the second law. Kepler's second law of equal areas. The Kepler's second law states that the radius vector drawn from the sun to the planet sweeps equal areas in equal intervals of time. Look at here. Here the two blue areas are equal. As the orbit is not circular, the planet's kinetic energy is not constant in its path. It has more kinetic energy near the perihelion and less kinetic energy near the aphelion, implies more speed at the perihelion and less speed, that is V minimum, at the aphelion. If r is the distance of the planet from the sun at perihelion, that is r minimum, and aphelion r maximum, then we can say r minimum plus r maximum is equal to 2a into length of the major axis. That is minimum radius plus maximum radius is 2a into length of the, that is 2 times the length of the major axis, that is r minimum plus r maximum equal to 2a. Kepler's second law can also be stated as the aerial velocity of a planet revolving around the sun in elliptical orbit remains the constant, which implies that angular momentum of a planet remains constant. As the angular momentum is constant, all planetary motions are planar motion, which is a direct consequence of the central forces. Now we'll discuss about third law. Kepler's third law, the law of periods. According to the Kepler's law of periods, the square of the time period of revolution of the planet around the sun in an elliptical orbit is directly proportional to the cube of the semi-major axis, that is equal to t square is equal a cube. The path of an object through the space is called its orbit. Kepler initially assumed that the orbits of planets were circles, but doing so did not allow him to find orbits that were consistent with Brahe's observation. Working with the data of Mars, he eventually discovered that the orbit of that planet had the shape of the ellipse, not a circle. Here, now let us do an example regarding this concept, that is the third law. By using Kepler's third law, find the orbital period of the object if its orbit has a semi-major axis 6 TAU astronomical unit. Here the formula T square equal a cube. Therefore, T equal square root of a cube, which is equal 60 into 60 into 60. So we calculate this. Now look at here. Square root of 60 into 60 into 60, which is equal 464.76 years. The time period having major axis 60, angstrom unit is 464.76 years. So far we discussed about the small history of Tycho Brahe and Kepler's, as well the law of planetary motion. We have done. Please subscribe our YouTube channel.